Welcome to today's paper reading. Today's paper is titled, Video Editing via Factorized Diffusion Distillation. This paper was published on AR14 by Uriel and colleagues from Meta AI. The authors introduce EMU Video Edit, EVE, a model that sets a new benchmark in video editing without using any supervised video editing data. EVE is developed by separately training an image editing adapter and a video generation adapter, both of which are attached to the same text-to-image model. To align these adapters for video editing, the authors introduce a new unsupervised distillation procedure called Factorized Diffusion Distillation. This procedure allows knowledge to be distilled from one or more teachers simultaneously, without the need for supervised data. This method is used to teach EVE to edit videos by ensuring precise editing of individual frames and maintaining temporal consistency among the edited frames. Additionally, the authors demonstrate the potential of their approach by aligning other combinations of adapters. The EMU Video Edit, EVE, model is designed for text-guided video editing, achieving state-of-the-art results on the Text-Guided Video Editing (TGV) benchmark. The core of EVE's success lies in the Factorized Diffusion Distillation (FDD) method, an unsupervised alignment technique that significantly enhances video editing capabilities. FDD employs score distillation sampling and adversarial losses to refine the editing process. EVE not only excels in traditional editing tasks but also in more complex operations like adding, removing, and altering object textures within videos. Additionally, the approach can be theoretically applied to any diffusion-based adapters, broadening its potential applications. Figure 1 introduces EVE, a text-guided video editing model capable of performing various editing tasks. EVE achieves state-of-the-art results on the Text-Guided Video Editing (TGV) benchmark, demonstrating its effectiveness in video editing. Additionally, the model enhances the evaluation protocol by incorporating ViClip metrics, which are temporally aware, providing a more comprehensive assessment of video editing performance. Figure 2 illustrates the architecture and alignment procedure of our model. We train an image editing adapter, in blue, and a video generation adapter, in orange, on top of a shared text-to-image backbone. The student network is created by stacking both adapters together on the shared backbone, in green, and aligning the two adapters. The student is trained using score distillation from each frozen teacher adapter, marked as SDS, and adversarial loss for each teacher, in pink. SDS is calculated on samples generated by the student from noise, and the discriminators attempt to differentiate between samples generated by the teachers and the student. Figure 3 presents a visual comparison of our EMU Video Edit, EVE, model against several baseline models using examples from the Text-Guided Video Editing (TGV) benchmark and its extension. The comparison showcases EVE's superior performance in terms of both objective metrics and subjective human ratings. Notably, EVE achieves state-of-the-art results across various metrics, demonstrating its effectiveness in text-based video editing tasks. The visual examples highlight the model's ability to produce high-quality, temporally consistent video edits that align closely with the input text instructions. This visual comparison underscores EVE's significant advancements over existing methods in the field of video editing. The initial approach to video editing involves stochastic differential editing, SDEdit, which adds noise to the input image and then denoise it while conditioning on a caption. This method preserves the general structure of the video but can lose crucial information such as subject identity and textures. A more dominant approach involves cross-attention interactions, where information from key frames is injected to ensure faithfulness to the input video structure. This is often combined with feature extraction, such as depth maps or optical flow. Another strategy involves inverting the input video using the input caption and generating a new video using the inverted noise, which adapts the InstructPix2Pix strategy to video editing. While effective, this approach can yield suboptimal results for various editing operations. Factorized Diffusion Distillation, FDD, is an unsupervised method designed to align adapters without the need for supervised video editing data. The training process involves a student model generating an edited video X0, which is then evaluated using score distillation sampling, SDS, lost by both the image editing and video generation teachers. To enhance clarity, adversarial objectives are introduced, leading to the formulation of specific loss functions such as LSDSedit, LSDSvideo, LDEdit, LDvideo, LGFDD, and LDFDD. These functions collectively guide the training of the student model and the discriminators, ensuring the generated videos are both temporally consistent and faithful to the input instructions. In this section, we discuss the experiments conducted to evaluate the EMU Video Edit (EVE) model against multiple baselines on the Text-Guided Video Editing (TGV) benchmark. The EVE model is specifically designed for editing tasks guided by textual instructions. The comparison with baselines allows us to assess the performance and effectiveness of EVE in this context. Key findings from the benchmark results highlight EVE's advantages and its implications for the TGV field. The performance of our model is fundamentally limited by the capabilities of the teacher models. Specifically, the editing capabilities of our student model cannot exceed those of the image editing adapter teacher. Additionally, our method requires the student to be initialized with pre-trained adapters. Training from scratch results in poor performance, indicating the necessity for teachers to be trained as adapters over a frozen text-to-image backbone. Future work should aim to overcome these limitations by enabling more efficient training and developing better performing models. Figure 4 demonstrates our model's capability to perform zero-shot video editing tasks that EMU Edit can execute on images, without requiring explicit training on these tasks during the alignment phase. This showcases the model's ability to generalize and apply learned knowledge to new, unseen tasks, highlighting the effectiveness of the alignment process in transferring skills from the teacher model to the student model. Table 1 provides a detailed comparison of various video editing methods against the TGV and TGV Plus benchmarks. The metrics reported include PIC-score, CLIP-frame, and VI-clip, which evaluate the performance of each method. Additionally, human ratings are included to show the percentage of raters who prefer the results produced by EVE, the method under evaluation. This table is crucial for understanding the relative strengths and weaknesses of different video editing techniques in a standardized and human-validated context. Table 2 presents an ablation study on the various contributions of our EVE model. The study reports human ratings on video editing results using the TGV benchmark, showing the percentage of raters who prefer EVE's results. Key findings include a 96.7% preference for the random init method, 77.6% for the method without alignment, and 84.2% for the method without discriminators. These results highlight the significant impact of each component on the overall performance of the EVE model and video editing tasks. The EMU Video Edit (EVE) model, developed using Factorized Diffusion Distillation (FDD), has set a new benchmark in the field of video editing. This method aligns adapters specifically for video editing tasks, significantly enhancing the model's capabilities. EVE now stands as the state-of-the-art in video editing. Looking ahead, there is considerable potential for applying this approach to other tasks and for further refining its capabilities. The authors are enthusiastic about the future contributions from the research community that will build upon and extend this work. Thank you for watching.